Maybe? Okay. Yeah, thanks for coming. So today we have Roohani. This is her first talk at IBM. Please talk. Please.
Thank you. Okay, so this is an algorithms talk. So I think, in particular, we'll be designing some kinds of algorithms using by proving some structural results about certain kinds of graphs. So that's like the theme. And it's a mouthful of a title. So I've also written it on the board in case you forget what we are doing. So in particular, so there are two things in yellow. These are the main parts of the talk. So the talk is about a problem. I'll define what this problem is. It's K to P minor free deletion, and we will be discussing this problem in a paradigm, and the paradigm is the paradigm of kernelization. I'll explain what this is. Both these things are. And then the things in red, these are mostly adjectives for the kind of kernelization that we'll be doing, and we'll be understanding all these three terms during, for example, the first half of the talk. So let's start with the problem. The problem is called K2P minor free deletion. K2P is a complete graph on two vertices on one side and P vertices on other side. And the input of the problem, it takes as input an undirected graph G and a positive integer K. And the question is to figure out if the graph has a set of at most K vertices whose deletion kills all K2P minors in the graph. So we want to hit all K2P minors in a given graph using at most K vertices. That's the problem, right? So the answer of the problem is always a yes or a no. Yes, if there is such a set, also called the solution of size at most K, and no otherwise. And this is an NP-hard problem, which means we do not expect any polynomial time algorithm for the problem. We do not expect to solve the problem efficiently, where the notion of efficiency is in polynomial time. Polynomial in the size, okay, you were right. Polynomial in the size of the input instance G comma K, the pair G comma K. Okay. So what we are interested in today is to design an algorithm for this problem that does not necessarily solve the problem. So it may be different from the kind of algorithms that you would have seen. It does not necessarily solve the problem, but our goal is the following. Let's say polynomial time is all you got. Then in polynomial time, can you determine some irrelevant parts of the instance? Parts of the instance that you can provably show are not relevant in deciding what the answer to the question should be, right? So this notion is also called pre-processing, or more formally, it's called kernelization. So what's a kernelization algorithm? It's an algorithm that takes as input, okay, the point, you see the pointer?
Yeah.
Okay. It takes as input an instance of the problem. In our case, the instance of the problem consists of a graph G and an integer K. And it's only allowed to take polynomial time. So it cannot completely solve the problem, an NP-hard problem, but it outputs another instance of the problem, which is again another graph G prime and some positive integer again K prime, with the property that the input instance is equivalent to the output instance. Meaning, if the graph G had a solution of size at most K, then G prime has a solution of size at most K prime, and vice versa. If G prime had a solution of size at most K prime, then G has a solution of size at most K. So if you wanted to find out the answer for the K2P minor free deletion problem on the instance GK, then it's enough to solve the problem on G prime K prime. Whatever is the answer on G prime K prime, that is also an answer for GK. So that's the notion of equivalence. And what we want is that the size of the output should be small. So we want to be able to spend polynomial time, start with a large instance, and say that in polynomial time I can get rid of some parts of the instance and come up with a small graph whose answer is the same as the answer to the original graph. So that's the notion of kernelization. So again, two things, that the size of, that the two instances are equivalent, and the size of the output instance is bounded. And it is bounded, and when I say bounded, I mean it's bounded as a function of k in this case. So the size of the output graph does not depend on the size of the input graph that you started with. You might have started with an input graph which is very, very large, maybe billions of vertices, and maybe all you want to know is whether this graph, whether there is a small set that hits all k to p minors in the graph, and that small is k. So we want the output graph, the size of the output graph to be bounded as a function of only k, and it should be independent of the size of the input graph. Is the paradigm clear? So this is a kernelization algorithm, and if there is such an algorithm, then we say that the problem admits a kernel, and f of k is called the size of the kernel. And if f of k is a polynomial function in k, then we say that the problem admits a polynomial kernel. And this is this polynomial here in the title, right? So we are interested in designing a polynomial kernel for k to p minor free deletion. And you may ask why polynomial, just because polynomial is obviously better than exponential always. And also for this problem, one can easily derive exponential kernels. So I mean, I don't want to talk more about it, but if you're interested, we can talk about it at the end of the talk. So exponential kernels are easy to derive. So we're interested in seeing if the problem can be reduced to an instance whose size only depends polynomially in k. So that's the paradigm. So this slide takes care of the definition, the paradigm, and what polynomial means here. Right? So just to move forward, before stating the main result of this talk, let me give you some background. So it all starts from a way more general problem than k to p minor free deletion problem, which is called the f minor free deletion problem. Think of f as some finite family of graphs. Right? So k to p minor free deletion is a special case of f minor free deletion when f is just a single graph, which is a k to p. So you can define this problem similarly. So you are given a graph G, a positive integer k, and you want to ask if there is a set of at most k vertices, whose deletion results in a graph that does not have any graph from the family f as a minor. Right? So this set hits all minor models of all graphs in the family f. And this is an interesting problem because it generalizes a lot of interesting problems in literature. For example, I don't know if some of you would have taken some algorithms course, you would know the vertex cover problem, which is the problem of deleting at most k vertices such that the resulting graph is edgeless. So this can be modeled as a k2 minor free deletion problem because after removing the solution, the resulting graph cannot have an edge, which is a k2. Maybe some of you would have also seen the feedback vertex set problem, which is the problem of deleting at most k vertices that results in a graph without cycles. So again, you can see that a graph has a cycle if and only if it has a k3. K3 is a triangle, a complete graph on 3 vertices. Okay? And so on. Again, it's not important for you to understand what these terms are, tree width, path width, and tree depth. Just think of them as some graph parameters. The purpose of this slide is to say that if you look at some graph parameter, for example, tree width, and you ask a question that can you delete at most k vertices such that the tree width of the resulting graph is some constant p, then this problem can also be formulated as an f minor free deletion problem. So this f minor free deletion encompasses a wide range of problems. And again, maybe another thing that you should remember from this slide is that the family f, so for example, if you fix this parameter tree width, if you look at tree width 0 deletion, this is exactly the vertex covered problem. And the family f that this problem corresponds to only contains k2. For tree width 1 deletion, the family f only contains k3, and so on. The point being that as you change this number 0, 1, 2, and so on, the family f changes with this number. So if you want, the problem of deleting at most k vertices to get to tree width 0 graphs is a different f minor free deletion problem, and the problem of deleting at most k vertices to get to a graph of tree width 1 is a different f minor free deletion problem, as you can see here. Right. So yeah, so that's the purpose of this slide, is to highlight this and the fact that the general problem is quite interesting on its own. And This general problem was studied in a seminal paper by Foreman, Lakshtarov, Mishra and Saurabh, who gave a very nice set of algorithms for this problem. In particular, they showed that this problem admits a constant factor approximation. So the optimization version of the problem, where you ask for a set of vertices of minimum cardinality which hit all F minors. This admits a constant factor approximation. For our purposes, we will mostly focus on the second part, where they also show that the problem admits a polynomial kernel, but in a slightly special case. So with respect to kernelization, their main result was this. They showed that F minor free deletion admits a polynomial kernel whenever the family F contains some planar graph. So F can be an arbitrary family, it's finite, and it can contain non-planar graph, but it should contain some planar graph. As long as it contains some planar graph, then this problem admits a polynomial kernel. So this is a quite general result, and this result, for example, gives polynomial kernels for all the problems that I mentioned in the previous slide. And what we need to remember for this talk is the nature of the size of this kernel. So the size of this kernel is polynomial in K if for any finite and fixed family F. So if F is fixed, this is a polynomial function of K. This becomes some constant, this becomes some constant. There are two features of this size that are interesting for the purposes of this talk. One is that if you look at the leading constants in this kernelization size, these leading constants are non-constructive. So if you ask me what is the real size of the kernel that I get, I can say it's order K to the power some function of F, but I cannot tell you what those constants are in the order notation, because these constants basically come from the well quasi-ordering theorem. So the kernelization algorithm uses arguments where they look at some minor closed graph classes, which by the well quasi-ordering theorem has some finite forbidden obstruction set. So the constants depend on the size of the graphs in this finite forbidden construction set, and we don't know this family explicitly for general F. So this is non-constructive, and this is actually the constructive thingy in the title, but this is non-constructive, not constructive. And the second important thing, aspect of the size of the kernel is the exponent of K. The exponent of K depends on the family F. So two natural questions arises, where can we get kernels where this leading constant is actually constructive, so the whole kernel size is constructive? And secondly, is this dependence of on F in the exponent of K, is it really important? Can it be avoided? So let's start with the second question, can this be avoided? So in a follow-up work of this work, Gyanapoulou, Jansen, Lakshtarov and Saurabh showed that no, the dependence of F in the size of K is unavoidable. In particular, they looked at the tree width P deletion problem. This is a special case of F minor free deletion problem when F contains a planar graph. And they showed that this problem cannot admit a kernel whose size is this. It's some function of P times K to the power P by 2 minus epsilon for any epsilon greater than 0. So basically they show that, for example, let's say I looked at the problem which was tree width 10 deletion. Then this problem does not admit a kernel whose size is better than order K to the 5. So P by 2, P is 10. Whereas tree width 100 deletion does not admit a kernel whose size is better than K to the 50.
When you say size, do you mean the number of edges or number of vertices?
The total size of the instance. So
number
of edges.
Okay.
Whichever is bigger. Right. So this answers that question negatively, if whether the dependence on F in the kernel in the size of the exponent can be avoided. But in the same paper, they also show a positive case. They showed that another special instance of F minor free deletion, which is tree depth P deletion. Again, these terms are not important. These are just some graph parameters if you don't know them. I will not talk about these terms after this slide. This is only for the literature survey part. So tree depth P deletion, they showed that this problem has a kernel whose size is G of P times K to the 6, meaning determining like tree depth 10 deletion and tree depth 100 deletion or tree depth 1000 deletion all admits a kernel of size order k to the 6. Right? So the asymptotic size does not depend on p. Can I say something, Colin?
No, just actually it's very funny that you have two parameters now and you're doing FPT kernelizations.
Yes.
But sorry.
No. But yeah, that's exactly what we're doing. Right. This work ruled out any general kernelization which is uniform, and here by uniform I mean where the exponent of k does not depend on the size of the family, in this case p, and this is where the uniform in the title comes from. But now what we are interested in, that this says that in general you can't have uniform kernels for F minor free deletion, but it also showed that some special classes of F minor free deletion can have uniform kernels, and we are interested in more special classes of F minor free deletion that can have uniform kernels. So that's where we are going with this. And before that, other than tree depth p deletion, the only other sub problem of F minor free deletion which admits a uniform kernel whose size is this is this F theta p minor free deletion problem, where F theta p is a family which is again a finite family of connected graphs, and you are forced to have a theta p in this family. A theta p is this graph. It has two vertices and p parallel edges between them. So if your family contains a theta p, then F minor free deletion also has a uniform kernel. So this is what was known with respect to uniform kernels: tree depth p deletion, theta p minor free deletion, and this brings us to our result. We showed that when a Fp minor free deletion problem, whenever this family F contains a K2P, again K2P is this complete bipartite graph with two vertices on one side and P vertices on the other side. We showed that when the family contains a K2P and all graphs in the family are connected, even then the problem admits a uniform kernel. So it's k to the 10. These constants have not been optimized. This is just for illustration purposes that the problem admits a uniform kernel. Right? And basically these are the three terms in red in the title. So we showed that this is the size of our kernel. It is polynomial in k. The leading constants are constructive, and the power of the exponent of k is uniform. It does not depend on the family. So is what we are doing clear? Right? And also,
Sorry, stupid question. So, isn't it the case that if you forbid K2P, then okay? Sorry, I'm spoiling stuff.
No. I was going to talk about this. So
okay.
Go ahead.
So
Okay.
if you forbid K2P, you also forbid theta p plus 1, I guess?
It's the other way around. If the graph does not have a theta p, then it should not have a K2P, because theta p is a minor of K2P.
Yeah.
But not the other way around.
So you might have a passive length 1, right? So that's the...
Yes, but you can only have one, isn't it? So
Yeah, that is also a very good point, and I will tell you, this seems like this is only a subdivision, and
Right.
but I will have a slide showing the technical difficulty of just this subdivision.
okay, thank you.
So again, just to also say this out, so theta 3 looks like this, and K2P is basically just a subdivision of theta p. Like you subdivide every edge once, and you get a K2P. So, and note that if the graph does not contain a theta p as a minor, then it also does not contain a K2P as a minor, because if you have this, then basically the theta p is a minor of K2P. So if you don't have this, then you also don't have this, right? So in that ways, actually, our result is a generalization of the previous theta p result. Why? Because so our result works. Because if you want to look at the problem which is theta p minor free deletion, then you can also in the family you can also add a K2P, because the solution is anyway avoiding a K2P, and if you're avoiding a K2P, then you can use our theorem. Okay, but yes, so just a subdivision, why things don't work, I will talk about it when I come to the technical part.
I get it now.
Okay.
Thank you.
Cool. Right, so this is the main result, and we will be talking about how things like this are proven, and I will mostly do some sketches. But before moving to the technical overview part, just one last slide. I just want to talk about further remarks here. So for example, maybe, for example, our result, it generalizes this problem, FP minor free deletion when FP contains a K2P. This generalizes the outer planar vertex deletion problem. What is the outer planar vertex deletion problem? Again, it says remove K vertices such that the resulting graph is outer planar. And we all know that a graph is outer planar if and only if it does not have a K23 or a K4 as a minor. Right? So this outer planar vertex deletion can be thought of as an F minor free deletion where the family F looks like this, K2P and K4, K23 and K4. And this contains a K2P for P equal to 3, so we can use our theorem to get a kernel for outer planar vertex deletion. And maybe one might wonder, why did we stop at K2P? Like, why not try to generalize it to KQP? In particular, what about K3P? Why not K3P, right? Of course, that's a very valid, fair question. It's just that if we had such a result which says that F minor free deletion admits a polynomial kernel whenever F contains a K3P, it in particular will encompass this problem. Planar vertex deletion. Again, planar vertex deletion is remove at most K vertices such that the resulting graph is a planar graph. And we know a graph is planar if and only if it has no K33 or no K5, so it is this F deletion problem. So if you have this result, it will also solve this problem and design, and again, which is still okay, it's just that designing a polynomial kernel for this problem is a notorious open problem. So if you can do this, it will be superb. Like, maybe we should all try to do this.
So there's no evidence that this can happen?
No. So no, this is still an open problem. Like a few years ago, there was a lossy kernel,
Right.
but
Is there any case of like non-planar F such that
no, not that I know. I mean, for example, I hope what I'm saying is correct. For example, even if the family just contains a K3P, nothing else. So this will not generalize planar vertex deletion problem, like it's just like K3P minor free deletion. I don't think I know what to do in that case.
Is it FPT in this?
Yes. I mean, you can definitely design some non-uniform FPT algorithms using this Robertson-Seymour.
Okay.
Because these are all minor, look at the class of graphs which are K vertex deletion away from being F minor free.
I see.
This is a minor closed graph class. So this is, well, quasi-ordinary theorem says there is a finite forbidden characterization for this. So it amounts to finding if there is such a minor forbidden characterization minor in the graph or not, and minor testing can be done in FPT. Okay. These are just some side remarks, and I think now we are moving to the technical part. So here is the outline of the talk. In the sense that, so the outline of the talk, what we do is something that probably a lot of people would do if they were trying to solve this problem. So I'm just going to tell you what a lot of people would try and do. Or maybe like there are some algorithms that try and do this, but I will tell you where the bottleneck thing is, and we will focus on the bottleneck part of the entire thing. So this outline, it may use some terminology that you're not familiar with, but it's again not important. Like I will just quickly go over what the outline is, and I will say what we want to do in this. Actually, let's not scare people. So let's just do this. So a lot of kernelization algorithms follow this outline. It starts by finding a small set. This is usually some approximate solution to the problem. So you want to solve the problem exactly if there is a solution of size at most k, but in a lot of circumstances, especially for this problem, there are constant factor approximations available. So you can start with some approximate solution. In our case, we'll start with a special kind of an approximate solution, not any solution. I will talk about that in a moment, but start with some approximate solution. You remove this set from the graph. This set anyway has bounded size, and you are left with several connected components. And in the kernelization algorithm, you try and now again, the goal is to output a graph which is equivalent and whose size is bounded. Right? That's the goal of kernelization. So then you try to bound the size, the number of components that you can have. After removing such an approximate solution, you try to bound the number of components by polynomial in K. And then you try to bound the size of each component by polynomial in K. If you do these two things, then the overall size is polynomial. General strategy, right? For K2P, bounding the number of components is not too difficult, but there are different arguments. I will not go into them at all in this talk. Right? So we start with a solution. We get some components, and I don't care about bounding the number of components. They can be bounded using some ways. We are not talking about that. But what we are interested in is bounding a size of a component, right? And again, to bound a size of a component, you fix a component C. In order to bound the size of a component, actually it's enough to bound the size. So let's say this set is some R. It's enough to bound the size of the neighborhood of R in this component. So if I'm able to bound the neighbors of R in this component, again, there are ways of then bounding the size of a component. Again, so I'm just gonna take the next 2 minutes for people who know this terminology. If you don't know, don't care about it. But for people who know this, this is a solution. This component has bounded tree width because it excludes a K2P, right? So you look at a tree decomposition of some nice tree decomposition of the graph. If the neighbors of R in this component is bounded, you just go mark some bag corresponding to all the neighbors. Like for each neighbor, you go mark a bag of the tree decomposition in which it's contained. You will only mark polynomially many bags. You take the LCA closure of those bags. This is still, the number of vertices involved in these bags are still polynomially many. And now if I remove these polynomially many vertices, if I look at what remains, the connected component that remains, they are what are called protrusions. The neighborhood of these paths is only in this. The neighborhood of these paths are not here because the neighbors of this part were marked. And the neighborhood of any part inside this is contained in 2 bags because I marked all the neighbors, I took the LCA closure, so whatever component remains, its neighbor can be in two of the bags. So its neighborhood is like 2 times the tree width. So this is a bounded tree width graph of boundary tree width, a boundary constant, and these are protrusions. And for this problem, if you find a big protrusion in the graph, you can actually shrink it. If you don't know this, no worries, we can talk about it in my office after the talk. But so what I was trying to tell other people is that for you to believe me that if we bound the degree of this solution, fix any connected component here, bound the degree of this set into this component by polynomial in K. If you do that, then I can assure you that I have a way of reducing the size of the whole graph to polynomial in K. Right? So that's the degree reduction. And degree reduction is what we'll see a sketch of degree reduction in this talk. So what comes next? I will tell you what this special solution is, number 1, and I will tell you the statement of the degree reduction lemma that we need to prove, and then we'll see the sketch of the things. So let's start with the first thing. In principle, any approximate solution is okay to start with. We will start with a special one because it will help us in degree reduction. So what is the special solution that we are starting with? This is called a one redundant solution. So it's an approximate solution which is redundant in the sense that if I remove any vertex from this set, the resulting set is also a solution. You might wonder why we're talking about redundant. At one point we're talking about kernelization and we want to get rid of redundancy, but on the other side we are starting with redundant solutions, but you will see that it is helpful. It's helpful, and also one can find such solutions whose size is not too large anyway, still polynomial, so we can start with these solutions. Is the definition clear? So think of it as some approximate solution with the guarantee that the whole solution is definitely a solution, but even if I don't pick one of the vertices in the set, the resulting thing is still a solution. Oops. Oh, sorry. And here is the lemma, which basically helps us find these redundant solutions of size quadratic in K. And we will start with this set. And so this will be like quadratic. I mean, there is an order thingy, but asymptotically quadratic. So what does this lemma say? It says that either I will find a one redundant set, solution or set of quadratic in K size, then we are happy, that's what we wanted as the first step, then you proceed to the second step. Or it says, or I will find you a vertex which is guaranteed to be present in every at most K size solution of your graph, every at most K size solution of the graph. But if I have such a guarantee, then I have a rule, like I have a way of reducing the size of my graph. So I start with this instance. If I know X is present in every K size solution, then I just remove K from the graph and I decrease my budget by 1, signifying that I have chosen to pick X in my solution and the resulting graph now find me a solution of size less than 1. So this happens, we are also great. And in the last case, it correctly reports that it actually solves the instance in some sense. It says that this is a no instance. The graph G cannot have a solution of size at most K, in which case also we are happy. So, So let me sketch how you prove something like this. It's not very difficult. There are different ways of proving it. I think the most convenient for me right now will be to assume that, which we know, to assume that this problem, F minor free deletion problem, admits a constant factor approximation even in the presence of weights. So if your graph, if the vertex set of the graph had a weight function, and the question was find a minimum weight set of vertices whose deletion results in a graph which does not have an F minor, for that problem also there's a constant factor approximation. It exists.
So that algorithm is randomized?
Yes, I mean again, for the purposes of this talk, let's use this. There are other ways of proving the lemma. I just find it easier right now to. So we can do it deterministically also, but let's assume this for this exists. Engine said this is randomized, which is true, which would mean that the lemma becomes randomized. But I'm saying that there are different ways of proving a deterministic version of it without relying on this. But for this purpose, for this talk, let's just use this one. So how do you start? You start by computing an approximate solution, like C approximate, where C is the factor guaranteed by this algorithm, constant factor approximation. You compute a C approximate solution, R prime. If the size of R prime is greater than Ck, then you know that every optimum solution of the graph has size bigger than K, strictly more than K. Because if the optimum solution has size more than K, then this is a C approximate solution. It will output you a set of size at most Ck. So if the size is bigger, then you just report that this is a no instance. G cannot have a solution of size at most K. Right? Otherwise, the size of R prime is bounded. So you start with this. Right? Now, what is the natural way of making it one redundant? You already have a solution to start with. You want to say that if I pick one vertex and if I throw it out, the resulting set should still be one redundant. The best way is to try to find, for every vertex in this set, try to find a solution that does not contain this vertex. Find that and put it in that set. Right? So this is what this is doing. And now how do I find a solution that does not contain a vertex? I'm using the help of weights. So in the instance, give this vertex a very, very, very large weight, like maybe a weight of K plus 1, and all the other vertices weight of 1. Right? And now ask, is there a solution of weight at most K? If there is one, it should not contain X, and if there is, if you say there is no solution of weight at most K, then every solution of size at most K should pick X. This is what this is doing. So for each vertex in R prime, you compute a C approximate solution that does not contain X. This is done using this weighted approximation scheme that I just mentioned. Again, if the size of this set is greater than Ck, then you can conclude that X is in every K size set. And if you conclude this, then you get this second condition of the lemma. Otherwise, the size of Rx is bounded. You have a doubt? So otherwise the size of Rx is bounded, and your final one redundant set will contain the original R prime and this Rx set for every original vertex of R. And this is one redundant. Right? So you can find one redundant sets nicely, and for the remaining purposes, we know that we have a one redundant set of quadratic in case size. Okay. So this is this figure that I was drawing here. So we have a set of size k squared. We remove it, we get some connected components. There are ways of bounding the number of connected components. And to bound the size of the connected component, I was trying to tell you that, believe me, that if you bound the set of neighbors of R in any connected component, then this will bound the size of the connected component. And for that, what we're gonna do is, and anyway, the size of R is bounded by order k squared. So what I'm gonna do is, fix a vertex x in R, arbitrary vertex x in R, and fix the connected component C of G minus R. We will bound the degree of x in C by polynomial in K. If for every vertex in R I bound its degree in C by polynomial in K, the overall number of neighbors will also be polynomial in K, because the size of R is polynomial in K. Right? So this is the goal. Fix x, fix C, bound this degree by polynomial in K. Uniform polynomial in K. Like this thing at the top should not depend on the family. Okay. So now degree reduction, right? So degree reduction is all we want to do. And now I just want to show you that if I was doing theta p minor free deletion instead of a k2p, why degree reduction is trivial, or rather the degree is already reduced. I don't have to do it. Let me try to convince you why. And here we'll see the power of a one redundant solution also, like why it's good to start with one redundant solutions. So if I was doing a theta p deletion, if you had a vertex x, let's say if the degree of x inside a connected component was at least p, right? If it was at least p, then you get a theta p minor by contracting this C, it's a connected component, into one vertex. There are p edges going on the top. Together with x, it forms a theta p. Right? But you know that R was a one redundant solution, which means that even if I don't pick x in R, the resulting graph should not have a theta p, because if R was a one redundant solution. So resulting meaning x union C should also not have a theta p. So the degree of a vertex is already bounded if you start with the one redundant solution. And then whatever machinery I was trying to explain earlier works to bound the size of the whole kernel. Right? But on the other hand, if I was doing a k2p minor free deletion, then it's not clear. Like x can still have a large degree. This is a component. We don't know how to get a k2p model of a k2p. So the point is that going from theta p to k2p, it sort of at least posed like a serious challenge, even though it's just a subdivision. Right? Okay. And now, so this is what we want to do. So this is the main lemma that we want to prove now. We wanted to do degree reduction. So x is some arbitrary fixed vertex in this set R. C is some connected component here. And we want to say that if the number of neighbors of x in C, which the degree of x in C, if it's very large, quantified very large here, not so relevant but very large, then I want to say that in polynomial time I will find an edge denoted by this green edge. This edge is an edge incident between x and one of its neighbors in C, such that removing this edge from the graph will not change the answer to your problem. So if I remove this edge, then if the input instance was gk, it's equivalent to an instance where the graph does not have this green edge together with k. So even if I remove this edge, the solution is not going to change, so you might as well work with this reduced graph. And the strategy is that you keep on doing this as long as the vertex of x, the degree of x in C is very large. You're always able to find such an edge which you can safely delete. So you keep on doing this until the degree of this vertex in C is not very large. And by not very large, meaning it's some cubic in K. The exponential factors, they are constant. So the exponential factor depends on the size of the family and not on parameter K. Okay. Okay. So now, if I were to prove this lemma, or rather, if I was deleting such an edge, what can go wrong? If I delete an edge, this will not make the problem harder. Meaning, if G had a solution of size at most K, then this graph also has a solution of size at most K. The same solution is a solution here also, because deleting edges will not create new measures. The forward direction works. In the backward direction, if someone gives me a solution of size at most K for this graph, right? If that solution already contained X, or maybe even this vertex, then that is also a solution for G. Because if the solution already picked X, then how does it matter if, if this solution already picked X, then removing such a solution from this graph or removing such a solution from this graph results in the same graph. The only edge that is removed is incident on X. Right? So the forward direction always works. The backward direction will not work, for example, when X is not in S. So the solution does not pick X, and now you have deleted an edge incident to X. Maybe that creates minor models of some forbidden minors, and that's the problem. And we'll try to address this. Right? So we'll come back to it once we now we are moving towards a structural lemma that we prove. We'll see what that is, and then we'll come back to it and see how that structural lemma can be used to identify the right edge whose deletion does not create problems.
Did we assume that FP is finite?
Yes. That's very important. Okay. Now, so this is the structural lemma part of it. So we take a break maybe from what we were doing and we'll use this. Though I don't plan to spend a lot of time on this break, so let's see. So this is what I call a chain structure in C. I want to say that inside C, there is a very nice structure that can be exploited. I want to explain what that structure is. And for that, again, I will crucially use the fact that your input solution was one redundant. In particular, I will use the fact that this X vertex that I had chosen arbitrary together with C is K2P free, just because R was one redundant. Okay. Here is the structural lemma. I don't plan to formalize it too much, but let me see what I can do with this. So, what does it say? X has lots of neighbors in C, because X had very large number of neighbors in C, right? That was the starting thing. And the neighbors of X are denoted by these red vertices. What this lemma says is that if X has lots of neighbors in C, then there exists a subset of those neighbors, and that subset is still large. If you start with a very large number of neighbors of X, there is still a large enough subset of neighbors of X which can be arranged like this. Now what do I mean by arranged like this? The neighbors of X can be ordered. These are the vertices which can be ordered. And there are paths between these two vertices, but so these are paths between these two vertices, like not necessarily disjoint or anything, just paths between any pair of consecutive vertices, and like these paths don't go from this portion to this portion. Like the figure really looks like this. So if I have to read this thing, it says like so it looks like this. So let me try to read this here as well. So it says that there is a large enough subset of the neighbors of X denoted by U1, U2, UR. This is also ordered. This is U1, U2, UR, such that between any two consecutive UIs, there are a neighborhood of X free paths. So NX free paths mean that there are paths that do not have any neighbors of X in it. If you see, these paths are not red in between. And UI minus 1, UI plus 1 is a cut between. So if you look at any UI and you look at the red vertices surrounding it, so UI minus 1 and UI plus 1, they form a cut between ui and the neighbors of x. So x cannot reach to any neighbor of x without passing through ui and ui plus 1. So there is this cut-like structure here. So there is ui, u1. There are some vertices that appear on paths between u1 and u2. Then there are some vertices that appear on paths between u2 and u3 and so on. And it looks like this. And the number of these ui vertices is large enough. If I started with very large set of neighbors of x. And yeah, and this is what I call a chain in the graph. Okay, maybe.
So this is under the assumption that you don't have a K to P.
Yes, I don't have a K to P in X union C. Again, just maybe very roughly, how do you get started in proving something like this? Or maybe from there it will also be clear the definition of what we're trying to do. How do you get started with proving something like this? It's not a full proof. It's just the starting point. So you have C here. And let me denote the neighbor of x with red. You start with an arbitrary neighbor of x. You see how many other neighbors of x can you reach from this vertex in this component. Yeah, basically yes, this. And just small things. So how many other neighbors of x that you can reach without using any other vertex of the neighbors, any other red vertex. So red is all the neighbors of x. So you just start with the neighbor of x. See which all other neighbors of x you can reach without using any red vertex. That's your first. That's this set. Then you start from this set. So there may be several vertices here. You start from this set and see which all neighbors of x you can now reach in the same way, where the internal paths do not have red vertices. You keep on doing this, right? And then you get a picture which is closer to that, except that, like, for example, if these sets that I get, these layers that I get, if these sets had like just one vertex, if let's say from here I could only reach one vertex, I would actually get what I wanted on the whole neighborhood set, right? But the only problem is that this may not happen, and a large part of a proof deals with it. So this may not happen, but the important thing is that these sets are not too big. This is really important. Why is it not too big? Because of K2P. Why? Because red vertices are neighbors of x, right? So if this set was very large, then you can, if for example, if the size of the set was larger than p, at least p, then with x, each of these p vertices, and contract this entire region to one vertex, you will get a K2P in x union c. So these sets are not too large, but we are still not done with that. If it's not too large, we need to do more things. But again, this is how you get started. And just for the purposes of this talk, you can assume that I was doing this process, and in this process, each layer turned out to be a single vertex. If each layer turned out to be a single vertex, then I get what I was sort of hoping for. Right? And an immediate corollary of this sort of a structure is the following. No, actually no, it's an immediate corollary of the later part. And another thing that you can prove is that this thing. This is also very important. So remember, we wanted to do degree reduction. We would have deleted some edges, and we got a solution of the reduced graph, and we wanted to see why this solution is not a solution of my original graph. This S thing. What one can show is that, again, that one can find a very large chain where such that if I remove some solution of size at most k, after removing the solution, this chain is pretty isolated, in the sense that after removing an at most k size solution, this chain cannot have neighbors to anything at the top. At the top was this R set, anything else except for S, X maybe. So it can have neighbors in X maybe, but nothing else. And this again, I can tell you how do you do this. So we already had some chain to start with, and I'm saying if this chain is large enough, then in this chain I can find a subchain with this property. And how do I do this? Right, there is X. Now let's say that if there was a vertex y which had neighbors to a lot of blocks meaning region between two consecutive red vertices. If a vertex has neighbors in, let's say, something like these many blocks, the point is, if it has neighbors in lots of blocks, then either x or y should be picked by a k-size solution. If not, if neither of them are picked, then a k-size solution can get rid of at most k of its neighbors of y. The remaining p neighbors still remain, right? And if the solution did not pick x or y, then these p neighbors together with x and y will form a k to p. Because all of these red vertices, they are definitely neighbors of x by definition of the red vertices. And if y had a neighbor inside a block, then that neighbor together with like one of the endpoints of that one of the red endpoints of the block will correspond to a xy path. Similarly, this will correspond to another xy path and so on. Right? So if y has neighbors to a lot of blocks, then this y should, either this y or x will anyway be deleted. Right? And note, we are only interested in solutions that do not pick x. If my solution picked x, because I was deleting an edge incident to x, if my solution picked x, I was anyway happy. So if it does not pick x, these y's will anyway be deleted. So the y's that can remain, so the potential y's here which can have neighbors from down here, are the ones which which do not see a lot of blocks. Right? So every y sees some at most k plus p plus 2 blocks, but then if the number of blocks is large enough, then for every y you mark these blocks which it can see. Right? You would have marked some polynomially many blocks that it can see, but then you can still find a large unmarked stretch of blocks, which will have the guarantee that there are no neighbors at the top after removing a solution. Make sense? Okay. So let's just remember this figure, that there is a large portion of the graph or a lot of neighbors of x that look like this, sort of exact. Anyway, the entire proof is going to be by pictures. So remember this picture, and remember that after I remove a solution, a set that hits all k2p, and a solution that does not pick x, then after removing the solution, this chain has no neighbors at the top except for x. And as a corollary of that, okay, let's not talk about this anyways for now. Right? So we have this structure. Now the question is, how do we exploit this structure? Like, right? And this is sort of, okay. And now we are getting closer to this degree reduction lemma. Like, how do we prove that? So for that, let me just assume one more thing. So let's say h is the size of the largest graph in the family, forbidden family. H is a constant. Right? So in each of these blocks, different blocks, in each block, let's say this is an ith block, look at all the graphs of size at most h which can be found as minors inside a block. Enumerate all graphs on h vertices, see if it can be found as a minor here, then put it, then yes. So you construct this family Gi for a block I. Gi contains all the graphs of size at most h which are present as minors inside this block only. For the purposes of this talk, again, let's assume that this family Gi is the same for every block. This is not a very, so the actual proof is based on induction. Induction on how many different GIs can you have. Like if I look at all blocks, some blocks will have the same family, but how many different families can you have? This is still a constant. It's a double exponential constant, but it's still a constant depending on h, because Gi is a family of all graphs of size at most h. This is some exponential function in h, and the number of different such families can only be doubly exponential in h. It's still a constant, so it's an induction based on how many different GIs can you get. But again, for this talk, let's assume that GIs are the same. If there is a minor in this block of size at most h, then that minor is also here, everywhere. Right? And now we are close. So we wanted to prove this degree reduction lemma, right? And in this degree reduction lemma, I was deleting some edge, right? To prove this degree reduction lemma, I will show you that, okay, I will firstly, for the cases that we are in of this talk, I will show you that if you pick the h plus 2th vertex in this chain, remember we had this chain, so there is this chain, if you pick 1, 2, 3 h plus 2th red vertex of this chain and you delete the edge incident with x in this vertex, then that's a safe rule. That does not spoil the answer. Right? And to prove that it is safe, I will show the following. I will show that you said that S was a solution of this graph, and if S was not a solution of this graph, then in G minus S, there is a forbidden graph which is present as a minor. I will show that there is a minor model of this forbidden graph that does not use this edge. If there is a forbidden minor that does not use this edge, then that means H is also present as a minor in this graph minus S, which is a contradiction to the fact that S is a solution. This is what I want to prove. Let's take 5 seconds. Yeah, 5 seconds over. Okay. And second last assumption of this talk. So we start with, so what we do, we have G minus S, we have H, and we have a minor model of H in G minus S. You start with some minor model of H, right? And this minor model definitely contains this deleted edge. Again, it's not a very big assumption, but let's assume that the minor model that contains X is just singleton. It does not contain any other vertex. If it's not, it's not a big deal. Is it okay? Is the assumption clear what I'm, that's it. Okay. Okay. And now we want to prove this. The very last assumption of this talk is, so we are looking at G minus S at the top, if you see, right? And there is a forbidden minor H in the graph, in G minus S. In principle, the solution could have intersected the chain, right? Let's assume it did not. Yeah, let's assume it did not for this talk at least. And now, the important point to see is that how are the branch sets of this forbidden minor arranged inside a chain? Okay. So these things are branch sets of a minor model of H, and I'm interested in those branch sets which intersect the chain. Right? So a branch set can intersect the chain, like there can be a branch set that takes some vertices from here and some vertices from the starting of the chain, but then it has to go via this cut vertex. So there is one such, there can be at most one such branch set. There can be at most one such branch set like this. There are no branch sets which intersect the chain and also the top part, because we know that after removing the solution, the chain does not have any neighbors in the top part except X. This was the third property of the chain that we showed. Because of this property, after removing the solution, this chain does not have any other neighbors in the top part. So these branch sets cannot occur. So the branch sets actually more or less look like this. The branch set that intersect the chain, they are either like this, and because these red vertices are like cut vertices, there are two kinds of branch sets. There are branch sets which are completely contained inside a block, and there are some branch sets which for some reason span a lot of blocks and go all the way to some other block to like get connected to branch sets which are inside the block. Like the branch sets look sort of as drawn in the picture. There are these long ones and there are some which are completely inside. The final question is that why do we have long branch sets? Why does this branch set needs to be so long? Why does this branch set needs to go all the way here? The only reason it needs to go all the way here is to connect to these smaller branch sets. Right? And here now the point is that if you look inside one block, if you look at just this portion of the branch sets, the yellow portion, this corresponds to some minor model of some graph on at most H vertices. Right? The same minor model also exists in every block because of our assumption. The family GI that I said is same for every block. the same thing can be replicated inside every block. So the point is, why does this block go all the way forward to connect with these things? These things can be recreated even in the first block. So you move this minor model around. You push back the long things and then redo whatever is happening inside a block in, for example, the first block. Stretch this thing all the way here, and basically you can rearrange the whole minor model and squeeze it in the front portion. And now the thing is, how many blocks have you used? Like, because there are not a lot of long minor models and there are at most edge branch sets, the number of blocks that you have used is at most edge. So in particular, and then there could be this one long thing which you're not able to squeeze because it needs to be all the way down here. But then, like for example, all the red vertices CX. What is like if this minor model used this green edge, I would rather replace this green edge with an edge from a previous red vertex to X. The role of the green edge is only to connect this branch set to a branch set on the top, and the only branch set at the top is the one that contains only X. And so yes, so this edge is really relevant. Like you can find a minor model without using this edge. Okay, I will stop here.
Thank you. Any questions?
I'm curious about how you say at some point, but you look at between two red vertices what set of minors you can create, and you say that you can reduce to a case where it's always the same thing. I'm curious about how this works.
Okay, I can also tell you later, but one line answer is it's induction. So the important point is that how many different, GIs. So for each block you have a GI. How many different GIs can you have? It's a constant. It's a double exponential constant, but it's a constant, right? So the induction is based on how many different GIs you can have. If you can have all possible GIs, then okay. So the induction is based on the following. So if the chain is long enough, very very long, then you partition the chain into consecutive pieces. Just partition into like large enough consecutive pieces, and if each consecutive piece has all the different GIs, right?
Yes.
If each consecutive piece has all the different GIs that you want, then you can do the same stretching argument, because whatever you want is present in every consecutive thingy.
That makes sense.
If not, then a part which does not have everything, it gives induction on the number of different things.
Okay, thank you.
Yes.
So in your key lemma on the finding irrelevant edges, the implicit constant is, I remember that it's double or triple exponential?
Double, yeah. At least double, yeah.
Then in your main theorem also the function g has same order of magnitude, or it is a bit higher?
No, it's not higher. Okay, let me just think about protrusions. I think when we say that eventually, so after we do degree reduction, I said that you can then bound the size of the component using known things, and the known things uses what are called protrusion replacers, whatever they are. They just take a large part, a special kind of large part, a special kind of a large subgraph, and replace it with a smaller equivalent graph. And I think that smaller equivalent graph that is replaced with, its size could be triple exponential in H, like the family. So one might have triple exponential at the max, but not more than that.
When the forbidden minors have disconnected graphs, then is there any hope that polynomial exists, or is there
No. So the okay, good. This F minor free deletion result, when F contains a planar graph, this big result that I mentioned in the very beginning.
Oh,
Yeah.
one like radio.
For follow-up questions, talk to Nathan. Where is Nathan? Already discussed the questions with him. So yes, so this works for any f without disconnected things. What am I doing? No, okay, sorry. This was this there is no condition on
I see.
f. But again, there is non-constructivity. I think the only reason we have connectedness is because of a thing that I had but I did not say. Like, I assume that the solution does not pick anything from the chain and I give you sort of a proof. But actually, we can prove that the solution may pick something from the chain, but what it picks is not too much. Only 3 vertices. And why do I get 3 vertices? Because if I have this structure, if the chain does not see anything at the top, then why is the solution picking more than 3 vertices? Because the solution can always pick u1, u2 and x. These are like the boundary of this chain to the rest of the graph. And this graph will, and like if the solution picked more than 3 vertices from here, then you can rather pick u1, u2 and x. If you pick these 3 vertices, you would disconnect this part completely, and this part is K2P free, right? But this argument will not work if you had disconnected obstructions in the graph. So that's the only place.
Any other questions? Yeah, if that, let's take the